All right, so what we want to do now is step back and take a look at the process of Gaussian elimination. What are we actually doing? Well, here it says that each elementary row operation in the process of Gaussian elimination corresponds to multiplication by a matrix. We know that Gaussian elimination consists of a sequence of row operations. And here we're seeing that Gaussian elimination actually corresponds to multiplication by a matrix. And the matrix can be read off from the form of the row operation. So let's look at this example to see what's going on. All right. So here we have a initial matrix, and let's perform a row operation. First row operation we want to do is to switch the two rows, the two first rows. Okay. So the new first row I'm going to call R1 prime. The new second row I'm going to call R2 prime. New third row I'm going to call R3 prime. And the original rows I'm going to call R1, R2, and R3. Right? So R1 prime is actually what you could call a linear combination of the original rows. As I said, R1 prime is actually equal to R2 because I've moved R2 up to the first position. But I can write that as 0R1 plus R2 plus 0R3. All right? So that's expressing the fact that R1 prime is actually equal to R2. The reason I do this is because we'll see later. All right? So what about R2 prime? Well, R2 prime is actually the original R1. I can write that as R1 plus 0R2 plus 0R3. And the final R3 prime, the new R3, is the same as R3. So I can write R3 prime as 0R1 plus 0R2 plus R3. Now, I can write that this way. I can write this in vector form. You see, this looks like a linear system of linear equations. R1 prime, R2 prime, R3 prime is equal to 0, 1, 0, 1, 0, 0, 0, 1, 0, 1 times R1, R2, R3. So that's why we say that the row operation is like multiplication by a matrix. Right? So let's go to the next stage. If I'm going to make this into REF form, what's the next thing I should do? Well, I know this has to be a leading one. So I should divide the first row by 2. Now let's see how that works. So I'm going to call this now R1, R2, and R3. Okay, so I'm going to reset my variable because this is what I'm working with. This is the matrix I'm working with, and I want to come up with a new matrix. So the new matrix, the first row will be half of this first row. So that means my R1 prime, my new first row, is going to be 1/2 times R1, which is my current first row. And there's no contribution from R2 and R3, so I have 0R2 plus 0R3. And the other two rows I leave the same, so I just have R2 prime equals 0R1 plus R2 plus 0R3. R3 prime equals 0R1 plus 0R2 plus R3. Now again, this looks like a system of linear equations where R1 prime, R2 prime, R3 prime is expressed in terms of R1, R2, R3. And I can write this matrix of coefficients this way. So again, I have that this ERO corresponds to multiplication by this matrix. All right. And then there's one more step. You can follow this one along also. What do I do to get from here to here is I need to subtract 1 times the second row. I'm sorry. I need to subtract 1 times the second. Whoops, what am I doing here? I need to subtract 1 times the third row from the second row. That's what I'm doing. I'm subtracting 1 times the third row from the second row. That will get rid of this 1 here. So the way we express that is that's R2 minus R3. And I'm replacing R2 by R2 minus R3. And we can see that here. R2 prime, which is the new second row, is equal to R2 minus R3. Once again, I can express this ERO as a matrix multiplying my rows of my original matrix. Now it's interesting that this process of multiplying by a matrix corresponds exactly to the multiplication of matrices that we've seen earlier in Chapter 1. Now, if you're familiar with the computational process of multiplying matrices, you can verify that these matrices associated with the row operations multiplied by the augmented matrix gives the next matrix in the series of augmented matrices that leads to the row reduced form. So let me remind you of that section here that, let's see if I can find this. Okay. This matrix multiplication that we saw in section 1.4.1, this is exactly the same matrix multiplication that we're doing here. So this is still also a composition of functions. So let's go back here. Whoops, sorry, I want to go here. So this gives us a way of comparing the process of solving linear equations to the process of solving an ordinary algebraic equation. All right. Now, for instance, if I have an algebraic equation 6x equals 12, I solve this by doing the same thing to both sides. Doing the same thing to both sides does not change the solution. And this is kind of a silly way to do it. You might as well multiply both sides by 6 inverse to get the final result. But he's just showing that no matter what operation you perform on both sides, you're going to get an equation that's true. Right? And the same thing goes when you reduce a matrix by Gaussian elimination. Here you start with, in the example that we've been seeing, we start with a system of equations that we can write this way. You could also write this in augmented form, but if we write this in matrix vector form, and here we have the matrix times the variables is equal to the vector of constants. So let me just refer you back to the augmented matrix we're looking at. We're just looking at this same augmented matrix here, right? We're just writing the constant vector on the right-hand side, and we're treating this matrix of coefficients as multiplying the variables. All right, so we're just writing the augmented matrix, breaking it out as a matrix vector equation. Then if you go back and look at the row operations one by one, here's the first one, the second one, and so on, we can perform that row operation on both sides by multiplying by matrices. So if we multiply this matrix by this matrix, we get this one. If we multiply this matrix times this vector, we get this vector. And this system of equations expressed in matrix vector format is still true. All right? So the sequence of row operations corresponds to doing the same thing to both sides of a matrix vector equation. All right? So that gives us a different insight into what's going on when we perform this system of operations. All right? And here we have finally the identity matrix on the left-hand side and a constant vector here. Now if we know we have identity matrix times a vector, that is the vector itself. You can verify, work out this matrix vector product, and that's actually what you get.